is based on plastic waste management, and I will be putting some light into the utilization of the plastic waste material in deriving some materials which can be used in electrical energy generation and storage. So before I begin, let us put some light into the top 10 global issues which have been highlighted by Professor Richard Smalley, who was at Rice University and who jointly, along with Professor Robert Curl and of Rice University and Professor Croto of University of Sussex, was awarded in the year 1996 for the Nobel the discovery of fullerenes, and his article in MRS Bulletin in the year 2005 highlighted the 10 global issues, and all of you can find that energy is at the top. Okay, so energy, then water, food, environment, and others are following. But 15 years it was more or less the same, and what we have observed from 2020 onwards and till date, this disease at number 7, it has jumped to number 1, which has been a major issue across the globe. And today, as per news, India is having uh, some 1,94,000 or more than that cases reported yesterday, and Odisha is also having more than 10,000 cases. So the scenario has changed, but still energy has been the issue, and it will continue with the depleting fossil fuels. So we are dependent mostly on the fossil fuels nowadays, and we have to look for alternatives, the renewable energy sources, deriving energy from that and storing in suitable devices, such that 50 years or 100 years down the line, we won't be facing severe issues or crisis of energy. So, what you will be expecting during this talk, I should discuss, means I will be discussing on some plastic waste. I will be discussing about materials which will be derived from plastic waste, some devices and utilization of these materials in devices for electrical energy, which can be generation or storage. And you are right. So these will be the outlines for my today's presentation. I will be discussing on this plastic waste. We will discuss about different types of carbons which have been prepared utilizing the plastic waste and devices. Before that, we will be having some discussions on the principles, fundamentals which we have already learned or we all are aware. Then finally, we will discuss about utilization in devices for this electrical energy conversion and storage. So, as for the definition which I have searched, and we all are aware that materials that are no longer needed and are thrown away, they are termed as waste. Okay. So there are various types of waste. At our home, we sometimes discard the food, sometimes we discard waste paper at our office or even at home, and these nowadays this e-waste that has been also a major issue. And is plastic waste, whether it be in the railway tracks or railway platforms, anywhere you can find plastic waste. And in the last couple of years, these PPE kits, those who have been which have been discarded, they are also raising the environmental issues. So these are all different forms of waste. Okay. So are there any solutions that we will discuss later? So these are some news which have been highlighted about plastic waste in 2020. there was one article by Center for Science and Environment that plastic waste is India's and world's most environmental challenge today, and the COVID-19 pandemic, due to the utilization of PPE kit, has made the matters worse. Then, uh, about 1 month back, there was one another article by NDTV that India's plastic waste generation more than doubled in 5 years. Okay, so as you can observe here, 34 lakh tons of plastic waste were generated in 2019-20, and it is 30.59 in 2018-19. So about 3.5 lakhs uh, tons of plastic has been added as waste in the year 2019-20. So are there any solutions? So we can term a waste as a waste if we are wasting it. Okay. So as per some person, you can have that there is no such thing as away. When we throw anything away, it should must go somewhere. Okay, so there is no such thing as away. When we throw anything away, it must go somewhere. So all of you might have observed people collecting some articles from the waste, and they are reutilized, or they go to make up some different objects. So we have all, most of us have experienced these carry bags which are made up of waste paper. Then nowadays, plastic bottles, this PET bottles which are discarded, fabrics have been prepared from that, and you can have these T-shirts which have also been prepared by these waste bottles. And recently, utilizing the biomedical waste from the PPE kit, some eco-friendly bricks have been fabricated. So these waste, they are going into some value-added products. So they are no longer waste. Okay. So now we will put some light into the plastic waste. So this is the cycle which you can observe, that from the polymer industries we get varieties of plastics. Then we will be having those products which will go into the users. Then they will discard it, and it goes into the process of collection. So it can come um, back when we reuse it, or we recycle it. So these are all some low value added recovery. Okay, and the worst option is incineration or landfilling or sea filling. So now let us come to the high value added products. That means utilizing the plastic waste, we can have these waste materials derived into some new materials which are having superior properties, better quality, and they are having some environmental value. So this is the upcycling of the plastic waste. So we have here high value added recovery, and we can have industrial symbiosis. That means some industry is preparing some materials from the waste or the byproducts of another industry, and it will be utilized as a precursor or raw material for some other. So in this regard, we have different types of carbon materials which have been derived from different types of plastic waste, and they have been utilized in energy conversion and storage, and this is a part of the circular economy. So in today's talk, mostly we will be discussing about the organic polymers. So as we know, these organic polymers, mostly they have carbon in their backbone. And if you observe here, we have polyethylene, polypropylene, polystyrene, and they have about 85 to 90% or more than that carbon content in the structure. Okay, so carbon has different polymers. Carbon has different allotropes, and we are also familiar with this types of allotropes like these carbon nanotubes, graphene. They are the most exciting research in the field of material science. So if we compare the carbon nanotubes, there are basically two types of carbon nanotubes. One will be your single world carbon nanotubes and another one is multi-world carbon nanotubes. So in case of single layer carbon nanotubes, what happens? You have a single layer of graphene. Whereas in case of multi-world carbon nanotube, we have multiple layers of graphenes as you can observe here. So this is one single world nanotube. This is one multi-world nanotube. You have several sheets of graphene which have rolled to prepare this multi-world nano carbon nanotube. So the catalyst is required for synthesis in case of single world, and in case of multi-world it cannot it can be prepared without any catalyst. It is single world carbon nanotubes. They are difficult to synthesize in bulk amount, so they are mostly expensive, whereas bulk synthesis is quite familiar in case of multi-world carbon nanotubes. So it's little bit expensive as little bit cheaper as compared to this single wall carbon nanotubes. Purity, if you compare this MWCNT, it is with high purity, whereas the purity is poor in single wall carbon nanotubes. So these are some of the points which we can compare between the single wall carbon nanotubes and multi-wall carbon nanotubes. So based on the processes which we are utilizing to synthesize the carbon nanotubes, they have their own qualities, they have their own efficiencies. So typically this arc discharge method is used, or you can have laser ablation method or chemical vapor deposition method to prepare these carbon nanotubes. So in case of arc discharge method, what happens? You have two graphite rods and you supply some current of few amps, and carbon will vaporize to form hot plasma, and you can generate these carbon nanotubes from that. Then you have laser ablation where your electricity is replaced by laser pulses, and um, from these two processes, completely different is your chemical vapor deposition, where we will be dealing with gases. Typically you can have methane which will be heated at high temperature, which will decompose. You have free carbon atoms which will be recombining to form the carbon nanotubes. Okay, so these are some of the processes and their comparison, their efficiency for the synthesis of carbon nanotubes. So what are the potential applications of carbon nanotubes? So this has been reported in one literature from there I have taken, and it's more or less true. So in present, if you have for large volume applications, you find these in battery electrodes forming some composites. Mostly these composites are with multi-walled carbon nanotubes, and for several sporting goods. Limited volume applications, you have this scanning probe tips. Okay, some medical appliances they are also using. If you talk about 10 years or less than that, they will be utilized mostly in those batteries, supercapacitors, some fuel cells, CNT based inks for printings. Then you can have these single tip electron guns, CNT sensor devices. Then if we think, let's say about 2020, 2030 or beyond that, so we can find their applications in power transmission cables, in nanoelectronics, even though they are also been utilized in nanoelectronics or others, but their utilization will be growing day by day. So What now we come to the CNTs for different applications, their production and their price. So this was reported in literature in 2014, and I am sure that the price would have gone down. So these single wall carbon nanotubes, as we know that they are expensive for the electronics purpose, which are used, their capacity, production capacity is much less, and when we go for the cheaper varieties of carbon nanotubes, mostly the multi-walled carbon nanotubes, they are uh, produced in larger volumes, and they are mostly used in different composites and batteries, or some other applications where they find suitability for electrochemical energy conversion and storage. So we have discussed about different processes, the production of carbon nanotubes. So basically, when we come to this synthesis of nanomaterials, there are two approaches. One is your top-down approach, another one is your bottom-up approach. So in top-down approach, what happens? You are having some bulk material which you will be breaking into fragments, and they will be giving you some nanostructures when you are breaking it down further. Whereas in case of bottom-up approach, we start with these atoms. So one can play around here to design the structure of these nanomaterials. You can have different types of additives. We can have different surfactants, different capping agents. So varieties of such materials have been utilized. So you can synthesize the nanostructures as per your wish. You can have rods, you can have spheres, you can have star shape, you can have different shapes of nanostructures when we are synthesizing from bottom up approach, and it gives us larger control over the purity, the morphology. So it's the advantage of bottom up approach as compared to this top down approach. So in case of bottom up approach, there are various processes. You can have chemical synthesis, chemical vapor deposition, just now what we discussed about the synthesis of carbon nanotubes, sol gel process, laser pyrolysis, aerosol process. Some biological synthesis approaches have also been utilized, where you can use different leaves extract, different flower extracts to reduce the metal ions to generate metal nanostructures. So what has been reported in literature for this synthesis of carbon nanotubes from polymer waste? So you can observe here the carbon nanotubes which have been synthesized utilizing the polyethylenes with malleated polypropylene and ferrocene as the catalyst. When it was carbonized at 700 degrees Celsius for 12 hours, these carbon nanotubes were obtained, and they were also characterized by Raman spectroscopy, by XRD, for confirming these carbon nanotubes. This scanning electron microscopy and transmission electron microscopy tools have also been utilized. So it's not only polyethylene, polypropylene has also been used to synthesize carbon nanotubes. One can generate these kind of carbon nanotubes using polypropylene with nickel oxide, this organically modified clays, and malleated polypropylene by heating them. And one thing you have to remember here, if you are going for this kind of synthesis process, the heating has to be done in inert atmosphere. If you are introducing oxygen into that, then the yield will be very less. So, or sometime you may not get this carbon nanotubes or carbon. So, mostly people have used argon. So, argon can be the atmosphere for synthesizing these kind of nanotubes. So, moving further, these utilizing polyethylene terephthalate, the PET, which is popularly used in preparation of this water bottles for our traveling or some other purpose we use. So these waste that can be utilized, and using some stainless steel mesh and heating it for pyrolysis in quartz tube. So these kind of nanostructures of carbon have been formed, and using polyvinyl chloride with ferrocene and heating it in in an atmosphere where pyrolysis occurred, and those kind of beautiful carbon nanostructures have been used. So it's not only tubes, one can also generate porous carbon. So if you are talking about this porosity, we can have three different types of pores. One will be termed as your micropore, where the pore width is less than 2 nanometer. So from 2 nanometer to 50 nanometer, it is mesoporous, and beyond 50 nanometer, if the pore width is, then it is your macroporous materials. So for these synthesis of porous carbon, one can use magnesium oxide as the template. Why magnesium oxide? Because magnesium oxide doesn't react chemically with this carbon under this environment. It is cheaper, it can be commercially available, and you can dissolve it in any acid once your carbon coating has been done or carbon has been formed over these structures. So it starts with magnesium oxide particles, whatever structures you want to prepare, that kind of template you have to take, then you have to form the composite with the magnesium oxide, followed by carbonization. So this contains your carbon over the magnesium oxide. Then you remove the template. So for removing the template, we need some acid. We dissolve the magnesium oxide, so carbon will remain as such. So the magnesium oxide template is more easily removable. That's why it is used. It is recyclable. Once you dissolve this magnesium oxide in any acid, then you can again utilize it for generating or producing magnesium oxides. So we can tune the size and volume of the resulting micropores. Okay. So people have also prepared these porous carbon from thermoplastic precursors. So these are the TM and scanning electron micrographs of magnesium oxide with PBA. Okay, so these porous structures have been formed, and apart from PBA, this polyethylene terephthalate and hydroxypropyl cellulose has also been used, where over the magnesium oxide, this polymer coating has been formed, and then it has been pyrolyzed to form this carbon coating, and then when dissolving this by dissolving this magnesium oxide in sulfuric acid solution, the magnesium oxide has been separated, and you can get only this carbon porous structure. Okay. So moving further, uh, carbon dots, about 3 nanometer size carbon dots have been prepared using polylactic acid waste. So polylactic acid, it has been uh, soaked in water at 95 degrees Celsius to degrade it to for the chain season to occur. Then this lactic acid, polylactic acid oligomers were formed, which were then heated at 180 to 240 degrees Celsius to form these carbon nanostructures. So as you can observe here, so these are the so this is the precursor degraded PLA, then this carbon dots which have been dispersed in the solvent, and this is dried one. Here one piece is there, one lump is there. So this is under normal light, and when you illuminate it with UV light at 365 nanometer, you can observe this luminescent behavior. Okay. So they have also performed the studies at different temperature, like 180 degree, 200, 10 degree, and to 40 degree, then for different time, and they have observed the emission from these kind of carbon nanostructures. So we discussed about carbon nanotubes, we discussed about porous carbon, we discussed about carbon nanodots. Now moving on to graphene. So utilizing the plastic waste which were processed by two-step pyrolysis, utilizing this nano clay along with this plastic waste. So first it was pyrolyzed at about 450, then around 850, 900 degree. The two-step pyrolysis process was done. Then it was washed, and this graphene oxide was obtained, which was then reduced to graphene nanoseeds. So this is the TM image of the prepared graphene nanoseeds. So varieties of materials can be synthesized from this plastic waste, which till now we are uh, familiar. Then we will discuss about device. So one side is our material, another side is our device. We want to utilize these materials with these devices, but before moving into the devices, we should have some connective link. So we should know how these devices will work, or what are the working principles, what are the concepts behind the uh, uh, working of these devices, or how to characterize them. So let's revisit the electrochemical concept. So in case of electrochemistry, mostly we deal with this electrochemical cell, where we have anode, cathode, and electrolyte. Okay, so at anode, oxidation of so these are some generalized characteristics. At anode, oxidation of metal uh, to an ion with charge will occur, so electrons will be released. So these are some examples of this oxidation process. Whereas at cathode, you will be having reduction. Reduction means electrons will be consumed. Okay, so there also there will be change in the valency. So we have one electrolyte which will be the ionically conducting medium in the electrochemical cell. So we have two types of electrochemical cell. One will be your galvanic cell, another one will be your electrolytic cell. So in case of galvanic cell, what happens? We will derive electrical energy from the chemical energy. Whereas in case of electrolytic cell, what happens? You will utilize electrical energy to perform some chemical reactions. So this is an example of Daniel cell, where we are having zinc ions. Let's say you take zinc sulfate in deionized water or distilled water, then you have this zinc electrode. Zinc will be acting as anode here. Based on the electrochemical series, you can decide which will be your anode, which is your cathode. So you immerse zinc in this zinc sulfate solution, and another side will be copper in copper sulfate solution. So you'll be having a salt bridge. Okay, so salt bridge, you can have this potassium nitrate or potassium chloride solution which has been gelled with agar. So that can serve as the salt bridge. Then what you will find, as soon as you connect these externally, you will observe current is flowing. And if you use one voltmeter, you can find that if this is 1 molar, this one is 1 molar, then at 25 degrees Celsius it will be giving you 1.1 volt. Okay, because zinc is minus 0.76 volt, and copper potential is uh, 0.34 volt, so it comes around 1.1 volt. So, so this is about the electrochemical cell. So how to characterize any electrode? In electrochemistry, typically one can find this cyclic voltammetry, one technique which is being used to characterize the electrodes, and it is dependent on the Nernst equation. So Nernst equation, all of we know that E is equal to E naught, the standard electrode standard potential, plus RT by NF. N is the number of electrons, uh, ln the concentration of the oxidized species uh, with respect to the concentration of the reduced species. Or if you convert into log scale, then this will be the relation. So what happens here, we will use one 3 electrode cell. Okay, so one will be your working electrode, then another one will be your counter electrode, and we have to use one reference electrode. So the reference electrode with respect to which our working electron potential will be changing. Then we have some electrolyte. Okay, so the reaction, oxidation reduction reaction, will occur in over the surface of this working electrode. Okay, we will be changing the potential, we will be cycling it. Okay, so here you can see ferrocene uh, which is reduced and it has been oxidized. So upon reduction, what happens, we will make the potential negative. So the concentration of the species near the surface of the electrode will change, and it will the potential will be dependent, and the concentration will be dependent on this Nernst equation. So according to the Nernst equation, you can know what will be the at what concentration what will be the potential, or what at what potential what type of concentration you are going to get. And then, and nearby the electrode surface, this species will start decreasing, so you will be having some diffusion layer, so current will drop. So current will drop, then again you cyclic it back. So from let's say zero point 0.3 to minus zero point 0.3, then again back to zero point 0.3. So that's why it is known as cyclic voltammetry. And as per the IUPAC convention, this, if you are scanning to from higher to low potential, there will be your uh, reduction here, and if you are going back from low potential to high potential, it is oxidation. So current will be changing accordingly. Then we will be as we will be discussing about the electrochemical cells, so we should know about the charge discharge process. So charging means we are filling it with energy, like if you are having some water bottle, if you are filling it, then you are charging. When you want to drink water, you will be taking water from that bottle, so we are discharging it. So similarly, in case of these electrochemical cells, you will be having charging discharging process. So externally we will apply uh, externally will provide energy to reverse the chemical reaction, that will be your charging. When you will utilize this chemical reaction to derive energy, electrical energy, that will be your discharge process. So if you uh, come across this lithium ion cells, so in lithium ion cells, what happens, your lithiated graphite, that will be serving as your anode. Okay, and lithium cobalt oxide, which is typically used, that will be your cathode. So lithium ions during discharge will be moving from this graphite anode to this lithium cobalt oxide. Then during charge process, what happens, these lithium ions, they will be moving from uh, our cathode to the graphite anode. Okay, and you will get some voltage accordingly during the discharge. So, okay, so now we will move into the devices, where we will find the applications of these materials which we have synthesized, or which are synthesized in literature. So mostly we will be discussing about energy, and there are various forms of this renewable energy we can have, which some of them are directly linked to sun, because sun is the ultimate source of energy. You can have solar power, wind power, and from there you can convert them to storage devices, because we are not getting sunlight 24/7. So we have to store it in some devices, to use batteries, supercapacitors to store, or you can use electrolyzers to store it in the form of hydrogen, which is generated and then later used in fuel cell to produce energy. So one such device is your solar cell, and I will be talking about dye-sensitized solar cells. So in this talk, I have taken only few examples, and what you can find in literature, there are many applications of these carbon materials, carbon derived from plastic waste in electrochemical energy storage, generation and storage. So in case of dye-sensitized solar cells, what happens? So this is different from the silicon-based solar cells. This is one electrochemical cell. So you have two electrodes. One will be serving as the photoanode, and another one will be your counter electrode. So in case of this photoanode, you have uh, one layer of transparent conducting oxide. Fluorine doped oxide is typically used, or you can have ITO indium doped oxide, because glass, which is the substrate which has to allow sunlight to pass through it, is non-conducting. So we want to make the surface conducting, but it should be transparent. So this transparent conducting oxide, TCO coated glass, is used. Over that, we have some wide band gaps oxide semiconductor like titanium dioxide, zinc oxide. Why wide band gap oxide semiconductor? Because we don't want these materials to directly absorb the sunlight. We want the dye to absorb the sunlight. That's why it is dye sensitized solar cells. So dye molecules will be absorbed on the surface of these nanoparticles of diode. Okay, so this will serve as the photoanode. Then we have this counter electrode where one catalyst, typically platinum nanoparticles, will be there. Then some space will be in between these two electrodes, which is filled with electrolyte, basically this iodide triodide electrolyte. So when light falls on this cell, what happens? Your dye molecules will be excited and they will be injecting electron to the conduction band of TiO2, which will be moving across the circuit. So this dye, which is now oxidized, will be reduced by this iodide present in the electrolyte to the ground state, and this iodide, which is converted into triiodide, will be reduced and regenerated at the platinum counter electrode. Okay, so there are some loss mechanisms also, that this electron at the TiO2, it may recombine with this oxidized dye or this triodide. But this has been a motivation from inspiration from nature, how this photosynthesis works, and it can also work under normal house lighting system. So this has been also shown here, showing some voltage under normal light, means this tube lights. So this is how the cell can be fabricated. You can prepare paste or the slurry of TiO2, then coat it, then sensitized with dye. Then you can have this platinum counter electrodes, which can be sputter deposited. Then you can have some polymers to seal the cell, and electrolyte will be filled. So uh, everything was fine till about 2012 or 13. Then what happens? There was a change in the history. This solar cells. Okay, that was evolution of perovskite solar cells, which has now been the leading topic in research in case of these solar cells. So as you can see, the first article which was published by Professor Miyasaka from Japan, has received about 15,000 citations in 12 years. So his first article, he had achieved very less efficiency, which was the converted into high efficiency solar cells by modifying the structure in 2012. So never be disappointed with your failure. That's the message. And from failure we can learn, we can modify it to achieve success. And now you can see it from about 14% or 13% efficiency which was reported, it is now about 25% efficiency in case of this perovskite solar cells. So these cells are similar to this dye-sensitized solar cells uh, in their earlier versions, but now they have been changed. You skip this mesoporous TiO2 structure. You have this fluorine oxide glass, over that perovskite is coated, then you have gold transport layer, and then you can have gold as the contact, and you can achieve a high efficiency with these solar cells. So we don't have sunlight um, throughout 24 hours. So we need some devices which can helpful, it can be helpful to us during the night time. So one part is your day, another part is your night. We have to take care of both. So in this regard, we have this story of the ant and grasshopper, that you have to store it for the time where you can utilize it. So we don't have the luxury of utilizing those devices, or they are extracting energy from them throughout the day. So some part we will store, and we will utilize that part during the other time where we don't have. So here comes the batteries as the storage devices. Our solar cells are the energy generation devices. Now we have batteries. So we have several, basically two types of batteries. If you classify, one is your primary battery, which once we use and discard it. Another one which we are using in our cell phones or laptops, they are secondary batteries. That means they are rechargeable. We can use it, you can extract the energy, again we will recharge it, then we can utilize it further. So this cycle continues. So this is the famous Aragon plot, which shows the difference between different energy conversion and storage devices. These different storage devices as compared to their specific power and specific energy. Specific power means how fast you can uh, extract the energy. Specific energy will be giving us an idea that how much energy we can extract from it. It is not the rate at which we will be extracting. Like you are running 100-meter pace. In that one, you will run fast. Okay, if you run fast, then you will win it. It will be your specific power. Then, if you want to run a 5 kilometer marathon, then you have to run slow, but you have to use more energy to run that 5 kilometers. So, if one car can go for, let's say, by one charging 100 kilometers or more than that, that depends on the specific energy. So these are some of the terminologies in case of batteries. You have the theoretical capacity, that 1 gram equivalent, which can deliver about 96,500 coulomb. And we have already discussed about the electrochemical cell charge discharge. Then you can calculate the theoretical energy depending on the potential and the capacity and the coulombic efficiency, how much you are charging and how much you are getting in the discharge. So the discharge capacity with respect to the charge capacity will be giving you the efficiency of the cell. So one example has been provided here for sulfur to calculate the theoretical capacity, and we will discuss about the lithium sulfur cell in the next slide. So most of us are familiar with the lithium ion cell, or somehow we have heard about lithium ion cell. So what restricts the lithium ion cells is that they are having a lower eh, capacity and lower energy density as compared to our lithium sulfur cells or lithium AR cells. Because if you go for these conversion type of cells, these lithium ion cells, they are insertion types of electrodes. So in insertion types of electrodes, what happens, you will be inserting lithium ion, extracting it, inserting it, extracting it, like that it continues. So it is restricted by the amount of lithium which is going into the cell. Whereas in case of conversion type of electrodes, your sulfur will be reacting with lithium to form lithium sulfide, and you can get more capacity in those kind of cells. So it is about 5 times what we can achieve in case of this lithium sulfur cells as compared to the lithium ion cells. So during discharge, you have this cathode which is fabricated using sulfur, carbon, and some binder. It discharges to lithium sulfide as the end product in steps. So octasulfur, this ring will open, it will form Li2S6, Li2S4, Li2S2, and finally Li2S, lithium sulfide during discharge. And during charge, you will be getting it converted to sulfur. This anode will be your lithium metal. So what happens? These Li2S4 and Li2S6, these higher order polysulfides, they are soluble in the electrolyte. So instead of staying at the cathode, they will move to the anode. Okay, so that will lead to decrease in the efficiency or decrease in the capacity of the cell. So what is required is we should prevent the soluble polysulfides to go from this cathode to the anode. So there are various approaches in literature. So the problems in those lithium sulfur cells are sulfur is insulating, and the product lithium sulfide which is formed is insulating. There is about 80% change in volume when we convert sulfur to lithium sulfide. Because then the subtle effect which I told, the movement of these polysulfides, then as compared to these lithium ion cells or other cells, it also have some formation of lithium dendrites, but it is less, and it can also show self discharge. So there are several approaches in literature to mitigate the subtle effect. We can confine the sulfur in some hollow structures, porous structures. We can coat the sulfur by carbon or some conducting polymer. Okay. Another approach is to put one layer in between the cathode and separator. So this is your electrolyte which will be soaked in some separator. You can have some porous polymeric separators or glass fibers based separators. So in between these two, here at this interface, we will be having an additional layer which is known as the interlayer. So these interlayers, they can be of some polymers, can have some graphene based materials, you can have carbon paper which have been utilized. So the fabrication of these cells starts with preparation of the paste for the cathode sulfur, or, with some conducting carbon binder and solvent. You prepare the paste, coat it on aluminum foil, and then you dry it, and you will get some sulfur loading. And finally, with an lithium anode, electrolyte, and some separator, you can fabricate these kind of coin cells. So the next one, which is another storage device, is your electrochemical double layer capacitors. So mostly carbon has been the preferred material in case of these double layer capacitors. So we can store the charge, and we can utilize it when it is required. So the requirement is that the material which will be used for this electrochemical double layer capacitors, that they should be porous, they should have very high surface area. Okay, so carbon satisfies this quality, and it is also cheaper. You can prepare various types of these porous carbons in bulk. So this is how these kind of cells work. So on one electrode, which is positive during charging, the surface, your ions will be coming from those electrolytes, and then this happen its process is reversed during discharge and the other cells. So this is your anion, and the other negative electrode, your cations will be going and they will be accumulating there. So this double layer will be formed, and then we will be discharging it. And this double layer thickness is dependent on the concentration of the ions which is present in the electrolyte, the type of ions which are using, and typically it is of the order of few angstroms. So we discussed about different materials, different concepts, principles, then different types of devices. Now we will visit the devices where these types of materials have been used. So I have already told about the preparation of graphene nanosheets from plastic waste, and it has been utilized in fabrication of dye-sensitive solar cells. So the graphene nanosheets which were synthesized, they were dispersed in a solvent and they were coated on the FTO glass. Okay, then over that this titanium dioxide layer was coated, and it was sensitized with dye with solid polymer electrolyte and platinum counter electrode. The research group, they have got some efficiency of about 0.2%, which is quite less, but the interesting thing is that they have utilized it in between these two layers, the FTO and your TiO2, to promote the bonding between them, and they have prepared the solid electrolyte based solar cells. Then in case of lithium sulfur cells, the plastic waste residue was utilized, and boron and nitrogen co-doped porous polymer, porous hybrid carbon separator was developed. Separator means which will be soaking the electrolyte, and it will be separating the sulfur electrode from the lithium electrode, and it was cycled for about 500 cycles, and you can see there is capacity decay of about 0.057 per cycle. So when they observed these kind of derived carbons, the porous structures in lithium polysulfide solution, so what they observed that this is after 30 minutes. So this is the Li2 S6, the lithium polysulfide solution. You soak this carbon, okay, nitrogen doped porous carbon, boron, nitrogen co-doped porous carbon. So what you will observe that after 3 hours the color is fading, and after 12 hours you can easily distinguish these two. This one is the polysulfide solution. This is that polysulfide solution with this boron nitrogen co-doped porous carbon. So the polysulfides are adsorbed. That means these are successful in retaining the polysulfide. That's why the capacity change is much less, and you are maintaining very high coulombic efficiency. Okay. So apart from separator, it has also been used as materials to capture the or trap the sulfur in the cathode. So PVC derived nitrogen and sulfur co-doped carbon has been prepared by using waste PVC bags, and along with that thiourea. Okay, and after calcination, this kind of porous structures have been used, and they were successfully utilized in these lithium sulfur cells. Okay, then some polystyrene foams, they have been treated with sulfuric acid at 180 degree for 2 hours, followed by washing, then treating with phosphoric acid, and then it was carbonized at about 800 900 degrees Celsius to obtain this type of porous structure of carbon, which is co-doped with sulfur and phosphorus. Okay, so that one was then utilized to contain the sulfur, and it was used in lithium sulfur cells, and the cells were stable till 800 cycles, and they retain very high coulombic efficiency. Okay. So we discussed about this DSSC, some applications in lithium sulfur cells. Then we have these materials, this plastic waste, which has been derived from polyethylene terephthalate. So PET waste, it was utilized along with organically modified clay, and it was heated. Then this kind of carbon nano seeds were prepared. They were treated with potassium hydroxide to get porous carbon nano seeds. So these are the carbon nano seeds, and these are the TM images of porous carbon nano seeds. So those were utilized in preparation of supercapacitors, the electrochemical double layer capacitors, and the capacity retention till 5,000 cycles was observed, and it retained about 90.6% of the initial capacity. So we have already discussed about utilization of magnesium oxide in preparation of porous carbon. So this polystyrene foam, it has been utilized with porous magnesium oxide to prepare the magnesium oxide polystyrene foam composite. Then it was carbonized. Then the magnesium oxide was dissolved in acid solution. Then the porous carbon flake was obtained. Over that, manganese oxide was deposited. So manganese oxide is also one active material for these supercapacitors. So it has a combination of now porous carbon, and with that we have this manganese oxide. So this was used in case of these supercapacitors. You can see these TM micrographs of the prepared samples, and the capacitance at different current density. Okay. And when it was cycled for 10,000 cycles, it was almost retaining of over 90% of the initial capacitance. So this is what we have discussed about different types of devices, applications of materials in these kind of devices. So I will now show some of my research activities in these types of devices, although they are not from plastic waste, but they work similarly to those materials which I have shown. So we have prepared carbon from sucrose by carbonization process, and using one tubular furnace, and under argon atmosphere at 1400 degrees Celsius, carbonization had occurred, and we achieved these nanostructures of carbon, which was coated on this tissue coated glass, and the coating thickness was about 1.3 to 1.4 micron, and it was used as counter electrode in Dyson stage solar cell. So as compared to platinum, where we achieved 5.8% efficiency, it was about 4.3. Then some metal nanoparticles have also been synthesized, and this is how we have prepared this platinum nanoparticles, and this is the mechanism how this these gold nanoparticles are prepared in literature, and how they are capped with some polymeric capping agents. So we synthesize these platinum nanoparticles of about 2 nanometer in size. Then we put it on this tissue glass, and then we fabricated these PSSCs, and we tested it for long-term stability. And what we observed is that uh, efficiency decrease over time is due to the dissolution of platinum, because platinum is known to be dissolved in this corrosive iodide triodide electrolyte on long-term storage, but the dissolution was more in case of heat and illumination as compared to if you store the cells in room temperature at dark. So we have also synthesized titanium dioxide nanotubes by hydrothermal approach using commercially available Degussa P25 TiO2, and calcining them at different temperature. So what happens? You have these kind of layers structures which will be formed of sodium titanate. Then when you wash with HCl, they will curve to form these TiO2 nanotubes. So these are the TM uh, images of the nanotubes which have been prepared and calcined at different temperature at 300, 400 and 500 degree Celsius. So if you increase the temperature, as you can see from here, the specific surface area decreases and the pore volume is decreasing. Basically the structure gets collapsing. So we prepared composites with sulfur, and then we utilized them in lithium sulfur cells. So what we observed that the titanium dioxide nanotubes which were prepared at 300 degrees Celsius, they were giving us higher discharge capacity and cyclic stability as compared to only sulfur or the TiO2 nanoparticles or uh, the nanotubes which are calcined at higher temperature. Then we have also modified the surface of titanium dioxide by reducing it using sodium borohydride, and the defects which are introduced to the surface, they were helpful in absorbing they were helpful in absorbing the polysulfides. So if you compare these titanium dioxide particles with sulfur to this BT, we have done this BT because the color of titanium dioxide is white. When we reduced it, it turned to black, so black TiO2. So BTS is having better cyclic stability and higher coulombic efficiency as compared to the uh, titanium dioxide particles. So let's summarize what we have discussed. We discussed about the different carbon materials. We having different morphologies which can be synthesized by different approaches from different plastic sources. So instead of discarding the plastics, we can utilize them for preparation of different types of carbon nanostructures, and they can be utilized in the devices like our solar cells, batteries, supercapacitors as electrode materials, and they are also as efficient as compared to others. So I am thankful to AICT for organizing this event, and ATAL Academy, and I am also thankful to CIPET IPT Bhubaneswar for providing me this opportunity. I also thank Dr. Ashwini Kumar Mahapatra and Dr. Santoshi for organizing this event. So thank you all. If you are having any queries, you can ask me or you can write in the chat box.
Dear participants, if you are having any queries, Dr. Mohanty is here. He will be happy to answer you. Yes, no questions. You can unmute yourself and ask, no problem.
Hello, can you hear, sir?
Yes, sir.
Ah, sir,
Yes, sir.
when you get nanoparticles, sir, so how do you,
Yes.
isolate? How do you make it pure from the other side products?
So basically, it depends on what type of nanoparticles you are synthesizing. Let us say we are going for synthesis of this TiO2 nanoparticles. Okay, you take the precursor like titanium tetra isopropoxide. Then you synthesize the particles. Then you have to wash it. Okay, so you wash it with suitable solvent to get rid of these unreacted precursors, and then you can centrifuge it to collect these nanoparticles. So this is how you can get these metal oxide nanoparticles. Or in some cases, you have to wash it with some like let's say you have this CNTs or some other carbon material. So you have to wash it with some what you can say acid or some other solvent which will dissolve the unreacted or undesired products, and you will get the pure product.
Okay, sir. Sir, you mentioned that the minimum temperature needs to for thermal, pyrolysis to make carbon nanotube is about 1000 degrees centigrade. So, has any new method for at a lower temperature been developed?
It depends on the catalyst. So,
Okay.
catalyst, as you know, it will decrease the activation energy. So, different types of catalyst, like for the CNT, typically nickel, cobalt, or molybdenum, cobalt, those have been used. So, you can lower the temperature by utilizing different catalysts, and maybe you can search through literature for some metal catalyst.
Okay. Thank you. Thank you, sir.
Yes, any other question? Because time is there, so you can keep on discussing, no problem. So if there is no further queries with you for this session, then we can conclude this session.
So
Uh,
thank you all for joining. So during this condition, pandemic condition, be at home, stay safe, take care of yourself and your family. Thanks for joining.
I thank Dr. Mohanty for addressing our participants. This presentation was full of information, knowledge based, and I hope all the participants have got more information about utilization of plastics for different applications, energy applications, and they are hugely benefited from this session. Thank you, sir, for giving your time and addressing our participants. Thank you, sir. Dear participants, thank you all for joining all the sessions till this till this event. And I'll be sharing, all of you are asking about the PPTs. I'll be sharing at the end of this program, because I think 2-3 sessions are remaining. So all these sessions I'll be sharing the recorded part. I won't share single PPTs. I'll be sharing the whole sessions recording part. So don't worry. And for tomorrow's exam, online exam, just prepare for some basic questions. There is nothing to be with each session, or more complicated questions will be there. Don't expect more detailed questions. Just prepare for simple basic questions. Everyone, just mark your attendance. Yes? Any query? Everyone, please mark your attendance, and we'll be joining for next session at 2:30.